I haven't set a strong date. I would think in 2 weeks would be roughly the time for first exam. I haven't set a date because I need to see how much we get through and kind of how folks do. I don't want to set a date and then it be too early. Programming note, I will be gone at the end of June. I will be gone 2 days for a conference in Salt Lake City. I will record lectures for that class. Like, I will go into the library, I will record lectures. Yeah. No, it's the summer, man, and it's like way too much time. Like, I will hold you like to read them. So, Michael, you don't have to be here because I'm not going to know if you're here. I can make Dr. Blanding come in and watch y'all. Right? So, I can also give you an exam during that time, which I may do. Saves class time. But that'll be something when we come up. All right, let's finish our lecture on timers. Remember that you have several timers on board your microprocessor. The timers are used, as they're just named, to time a variety of things. The most simple thing is simply to set a timer to go off periodically. So maybe you have some sort of frequent event you need to do. Maybe you need to switch tasks. Maybe you need to wake up every couple seconds. You can set a timer to do a fixed sort of periodic polling. You can also use timers to measure the frequency of waves, the duty cycle of waves. You can use them to generate square waves. There's a lot of different functionality. On your particular board, there are 4 timers, and they are memory mapped to these locations. So remember, when you want to talk to some device, you need to know its base address, and then you need to know the offset of the individual registers. Go to Chapter 5 in the reference manual, and that gives you the address of all of the devices. Remember, when we're talking about the structure of the timers, the major registers that you need to deal with are the control registers. That governs, does it count up, does it count down, is it in up-down mode, what's going on. You've got the count register, which holds the actual current value of the timer. You have the top register, which sets an upper bound for your timer. And you have a prescaler for the clock. So what we'll talk about a little bit today is the variety of clocks you have. We really will not mess with the clock system except to choose a prescaler value. And so remember, when you go to choose a prescaler value, it has to be a combination of the prescale and the value such that you can time the actual duration that you want. So again, 4 primary registers we will deal with. The timer objects actually have many registers. They have a bit more than the other devices. There's, I think, about 20 on each of them. You only need to really deal with these 4. Now, there are a couple other important registers when dealing with timers. We are going to start to deal with interrupts when it comes to timers. Every device that supports interrupts has sort of 3 particular registers associated with the interrupt functionality. The IEN register is the interrupt enable register. So your device will support a variety of interrupts. You have to enable and disable those interrupts. When an interrupt occurs, if it's enabled, the processor will then service that interrupt. So there will be a special function that you call, that you go to, that will occur when that interrupt happens. You don't need to take care of that. The processor itself will automatically find the interrupt and service it, but you first have to enable the interrupt. The second register is the IF register. That's the interrupt flag register. When an interrupt occurs, there is a particular bit related to that interrupt that goes high. That is what actually tells the processor that an interrupt has occurred. For an interrupt to be serviced, it must be enabled and the flag must go high. So the interrupt flags will always go off. They will always go off regardless of whether the interrupt is enabled, but the interrupt will only be serviced if that interrupt enable bit is set. Now, the final thing is the IFC register. It's the interrupt flag clear. Once an interrupt flag occurs, you have to tell the peripheral that you have done servicing it. You have recognized that the interrupts occurred and you've done something about it. you have to clear that interrupt flag. And so you do that with the IFC register, where you write a single bit to that register. If you do not clear the interrupt flag, you will constantly have to deal with the interrupt. You will stay in an infinite loop in that interrupt service handler. So you need to make sure that whenever you're in an interrupt, the first thing you do is clear the flag for that interrupt. It ensures that you don't keep coming back there over and over and over again. Other things about the timers, remember we have the data structures that we can use to access the control, the command, the status register, and also the interrupt enable and the interrupt flag registers. Lab 1 has you access the GPIO via pointers. After that lab, once you've done it, you've convinced me you can access everything purely by pointers. You can use the data structures going forward. So everything after Lab 1, just please by default use the data structure that it provides. It will make your life easier. Couple basic things that you need to set up when using a timer. You need to set up the clock that it comes from. So remember, there's a variety of clocks that they can source. You need to set the prescaler on that clock, and then you need to set the mode for that timer. Is it counting up? Is it down? Is it PWM capture? What is it? One final thing that we need to do, at least for in our class, is enable debug run, such that the timer is active while you're debugging the chip. These are the 4 sort of primary fields that you need to set for the timer. What I'm going to generally do for the first couple peripherals we talk about is I'm going to tell you what parameters you need to set, and then I'm going to tell you sort of what setting you want them to be. What your responsibility is to figure out, well, what bit field is that a part of? So out of the clock select, if I want to set this, what is the bit field that I want? And then what is the hex value that I put there to do that? So the question is, mode is which bits of what particular register. And if I want to set the mode to up, what is the actual value that I write into that field? So what I want you to do is go to pages 543, 544, and look these up. And I want this row to do clock select. I want this row to do the prescaler, this row to do the up, and this row to do the debug run. So chat with each other, show where you find it, but you need to figure out what is the bit field and what is the hex value that you actually want to set it to get that functionality. All right, let's take a look at what you've got. So guys up here, clock select. If I want to set it to, this means the high frequency peripheral clock, what bit field is that? What bits is that a part of?
So that's bits 16 and 17.
Okay, so bits 16. Let me pull this over. So bits 16 and 17 in the control register are the clock select bits. What do I set that to if I just want the high frequency clock? 0. So what you want to do is for every one of these registers, you're going to have all these definitions. And if I want to set the high frequency clock to just be the clock, I set it to 0. That is already the default value, so I don't have to do any of these things. Generally, the register's default value is going to be 0, and they're going to set up all the fields to kind of make sense for 0. Sometimes, though, it might not be 0. Like for different communication peripherals, it might be set to a different number rather than 0, rather than off. There might be a special bit there. But when you're looking at the data sheet, this tells you that the prescaler, or sorry, I'm looking at clock select. The clock select is this clock already selected out. So it's bits 16 and 17, and it's already set to 0. All right, so what do I, Jason and Kyle, what do I want the prescaler to be? If I want it to be 1024.
24 and 27 bits.
right? Yep, so 24 to 27. And if you want the value to be 1024, then you put integer value 10 there. So this is not 2, this is an integer value. So you would write hex A into that field to get that result. All right, Ben, how do I make it be in count up mode? What bits are those? Oh, Ben Dimchek, sorry. I get 2 bins. Did you guys find that one? Right, so the mode here is 2 bits. It's bit 0 and 1. If you think about it this way, there's 2 bits. That means there's 4 modes that I can be in because I only have 2 particular bits. So if you go down here to the bottom, you can see for the mode, if you want to set it to 0, 1, up, down, or the quadrature mode. All right, Bill, last one. How do I enable debug run?
Bit 6.
Okay, bit 6 here is debug run, and the timer is running during debug mode. So what that means is while you're debugging, if you set a breakpoint, your timer is actually still kind of running. You can turn it off. You can do what you need. But this is going to be some functionality that you want to make sure that your timer is actually running while you're debugging your chip. All right. So let me get that off the screen. Darren, yeah.
So could that cause problems? Like if you have an interrupt that, say, needs to be serviced every second, and you hit a breakpoint, and then you want to step through your code, but then it's just going to jump to the interrupt?
Yes. So when you have sort of an event-driven system, like with interrupts, like your interrupt is supposed to be handled as quickly as possible. If you're in a breakpoint inside the interrupt, what could happen is the timer could just keep going. But there's still only going to be one interrupt. The same interrupt does not stack. If there were multiple interrupts, they may stack. But let's say that you're sitting in the timer 0 interrupt and you take forever and the interrupt occurs again, you'll just end up right back where you were. But given the applications we're going to deal with, like that's sort of normal behavior. Like if you're supposed to blink a light 3 times a second, by the time you hit go after your breakpoint, you should already be back in the interrupt handler. So it does get to be funny when you're using breakpoints and you've got interrupts because the rest of the chip is running. It's going. If it gets to be a problem, you can turn off debug run, and if you don't want to have that behavior. Good question. All right. What you have, so for all of our peripherals, what a good practice is going to be, and when we get to SPI and I2C, it's going to be much worse, is you really want to make a table of what are my fields, what are my desired values, what are my bit widths, and what are my actual values that I want to write in. What this table helps you do is figure out how you actually write the bit masking and shifting code to make this happen. So what you want to start saying to yourself is, this is a 2-bit value. That means my mask is going to be 1, 1, which means it's going to be 3. This is a 4-bit value, so that's going to be F. This is a 2-bit value. That's going to be 3. This is going to be a 1-bit value. That's going to be a mask of 1. So what you have to do is that if you want to write a 0 into a register and the value's already 0, you don't have to do anything. If the default value is acceptable, you don't need to write in a 0 anywhere. You can't actually write a 0 on top of a 0, like the chip will not detect that as a change. So if the value's already there, there's nothing that you need to change. So all that we really have to do to set up this timer is to write to the prescaler and write to the debug run. The prescaler is a 4-bit field, so when you are going to AND it with the mask is going to be F because that's 4 little ones. Debug run is a single bit, so that means that the mask is going to be a single bit. For Lab 1, who has gotten through sort of task 3 where you're doing all the pointer math and can AND things? So you've gotten okay with ANDing and the bit masking such that you should be able to talk to this peripheral. So the idea here is this is generally what your code is going to look like. Well, you're going to use the data structure and you're going to say, I want to modify the control register. And so what you do is you read in a copy of the control register and then you modify it and then write it back. So you're going to have lots of lines of code that have this general structure. You're going to read the register. You're going to AND it with some sort of mask that is shifted over the proper distance. So if I have a register and I AND it with 0000F, that is going to kill all the bits except the lower 4. Maybe it wasn't those lower 4 bits that I wanted to get rid of. Maybe I actually only wanted to modify bits 24 through 27. So the key things that you need to figure out is what are the masks, what is the shift, what is the value that I want to write in, and then how much is that shifted. And super hint is that this and this are always going to be the same value. The shift is always going to be the same. So who haven't I talked to today? Nick is here. He's gone forever. Joe, if I want to write this field, what is the mask that I'm going to put here? F, because it's 4 bits wide. Jason, if I'm going to try to write to the prescaler, what is my shift value? How much do I actually want to shift that mask over? It'd be 24. So what you want to put here is F, because it's a 4-bit wide field. What you want to put here is 24, because you're going down the register 24 bits. Felix, what's the value that I want to shift in? All right, so we want to set the prescaler up. For the previous slide, we said that we want the prescaler to be 10, decimal 10, which is hex A. So that's the value that I want to OR in. How much do I shift that value down? Say what? So 4 is the width of the mask. I am putting that value in the same place that I'm masking off the bits. So this shift value will always be this shift value. So it'll be 24 bits down. So your mask is equal to the width of the field. The shift is the starting position of the field. And then the value is the value that you want to put in. And the value should be of the same width as the field. Am I right, Professor Haig? So when you fill out all of this code, you're going to have lots of code that looks like this. And remember, some of you, I had conversations with people last Wednesday, like, why do we write it as this little squiggly line, and do we invert it? It's because if you wanted to mask this out, every time you do it, you have to write F, 0, 0, 0, 0, 0, 0, 0, all the way, no, you have to write F, 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 0, F, 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 all the way down to get the right mask. This sort of structure you can use to modify any arbitrary register. So you can imagine writing a function that takes as an argument a pointer, a mask, a shift, and a value, and you can have a function called write register or write field, and it will do it for any arbitrary register. So that means is that when you're setting up the timer, you can have a bunch of calls that say write this value to this register with this field at this offset, rather than writing this line of code over and over again. That is, and you write the code this way such that it can be turned into a function. Ben?
Does it do the and then the or?
No. Yes, this is the correct order of operations because the and is first. If you wanted to be extra safe, you could put in the parentheses. And I would just do that just for the sake of completeness to make sure that it's done in the correct way. Okay, yeah, you don't want to or this over. This is going to get resolved first, then sort of going left to right, and I think and has priority over or. That will occur first. That's a good question. Okay, this is an important concept in class. How we got from this table saying I wanted 1024 in this field, which means I'm talking to these bits and I'm putting this value. going from that statement and translating it in to this line of code is like the fundamental activity for the rest of this semester. So if you can't figure out how to set up your peripheral, you're never going to get them working. So if this is confusing, if this isn't making sense, you need to get that resolved quickly. Because later on I'm just going to say set the clock polarity and the clock phase on the spot of these values, and I'm going to expect you to figure it out about how to do this. So these 3 or 4 slides are important. This is what my code looks like in practice, and to Ben's comment, I do have the extra parentheses there just to make sure nothing blows up. One important thing is make sure you're actually talking to the control register and not the count register. They're named very similarly, and if you're using sort of control space to do the intelligent completion, it might be really easy to accidentally select the first thing that starts with C, and you'll end up at the wrong register. So make sure that when you do this, you're actually talking to the control register and not the count register. Now, there is a little shortcut when it comes to doing single bits. So if I am going to do a single bit, my mask is 0, 1, and the shift is just the position. So if you are doing a single bit, you can perform these operations right here. So you can simply read the register and OR in the bit in the correct position. If there was a 0 there, it'll now be a 1. If there was a 1 there, a 1 will remain. The same way, if you want to clear a bit, you are simply going to just AND it with the mask. There's no point to OR in a 0. ORing in a 0 does nothing. It logically has no function. So if you wanted to if you wanted to set a single bit, you could write this line of code here to set debug run. Or if you wanted to truncate it, you can truncate it down to this. This is sort of the OR equals operator. So it's kind of like the same thing as like a plus plus or a plus equals. This is probably the most straightforward thing. When I see something of this format, I say, oh, they're setting bit 6. Like it's a pretty common thing to see when someone wants to set a particular bit, they do this. And if you were going to clear a bit, this would be an AND with that mask. It's like you're forming a question. Yes?
Is it possible for the value pointer? Never mind, I had an idea. But
Okay.
I think it worked out.
Okay. Was it an optimization or was it a problem?
No, it was like a timing thing where the read modify right, where the pointer changes while
You can't avoid it. So the pointer will always be volatile, which means this isn't cached. But no matter how you write this line of code, you're still reading a value, modifying it, and then writing it back.
Yeah.
So 1, yes, it could change in that amount of time.
Yeah.
That's the nature of the system. 2, if you use the bit banding region of memory, it's guaranteed to happen atomically. So if you're worried about the value changing, you access it in the bit banded region, and it'll do this atomically. So it'll make sure it happens in one transaction. You're not really going to have, when you're configuring, so the first time you configure the timer, like it's not an operation. So you shouldn't really worry that someone else is going to change it.
Yeah.
The only time that there might be conflicts is if you have another device writing to your device, which may or may not happen, or if you're trying to read a buffer from a device that's getting data. But there are extra buffer registers that sort of queue that up so that you don't get the raw data. You get the buffered data, which has already sort of been latched. Like you're going to be fine. Other questions? So Ben's fundamental question was, what happens if this changes between here and here? Well, it can happen, and that's the trouble of dealing with an embedded system, and you just have to be prepared for weirdness to occur like that. How do you protect against it? It depends on the...
I ran into this problem a number of different times working on embedded systems where things was changing every so often. You might only see it 65,000 times, and so it's very, very sporadic.
So what was going on? This was your bowling ball project, yes?
Yeah, I was doing 16-bit addition and 8-bit, 16-bit addition with overflow in an 8-bit system.
Mm-hmm.
So every once in a while, it would miss the lower counter would roll over. I wouldn't know the whole thing rolled over. I had to just turn off interrupts and things like that. But.
No. So if you're really worried about something happening in your system, the default behavior is to turn off interrupts. You turn off interrupts, and then the only thing that happens is what you order it to happen. Now, your peripherals might change if they're receiving data, but nothing else really goes on. Turning off interrupts means your system doesn't respond to anything after that. So the challenge with embedded systems is and what you'll see this in Lab 2. Lab 2, you're not going to have any code in main. Like, you're going to have some setup code, and then everything else is going to be an interrupt handler. And they're going to be changing shared variables, and they're going to have to work with each other. That's kind of easy when you step through it, it makes sense. But when you tell it to run and you let it go, it runs by itself. There you go, little computer. It'll run by itself. So the challenge with embedded systems is that these things are happening in real time, not in CPU time. So when you're working on your desktop, you have complete control of what's going on. Here you have external things that are happening and things that are independent. So you can turn off interrupts. You can access things in a bit-banded manner. And you also design your system such that if you're reading something, no one else should be writing to it. Like, you don't want, it's called the producer-consumer sort of reader-writer problem. You only want one person ever writing to a memory location at a time. And you can use locks if you really wanted to keep that like that. But you're the only one on here. And with the bit rolling over, when we discuss sort of doing the data types with like uint 16, uint 8, be cognizant of that. If you, in your function, declare something to be a uint 8 and you pass it 1024, it's going to show up as 0 because it's the lower 8 bits are going to be 0. So again, I had a student last spring doing a Fitbit. She was making a counter. She was trying to display the step count. When she walked around the building once, the step count would go up to like 120 or so. I had her walk around the building twice. It went over 256. So her step count rolled over back to 0. Not because the internal value was wrong, but because the function parameter used to display the code thought it was a uint 8. So she passed it a 16-bit value, but it was truncated down to 8. So you get into these wonky things when it comes into embedded systems. Nick is back. York Exponential got a grant. How much money are we talking about here? $6 million. Woo, that's some good change. What do you get of that? No. When dealing with the timer, we looked at the control register. That's where you set up all the values. To start and stop the timer, you use the command register. A lot of these peripherals are going to have command registers where you tell it to send a packet, read a packet, send a start bit, send a stop bit. So this one has a command register that simply does two things. It starts the timer and stops the timer. You have to write a 1 to start to make it start. You don't stop it by writing a 0 to it. It really doesn't detect writing zeros. So you write a 1 here to start to make it start. You write a 1 to stop to make it stop. That's how you start and stop the timer. It's pretty straightforward. Now, here's sort of the first challenge you're going to have when it comes to timers. We went through this whole machination about like how long can we time something and for how long. We did that because let's say that you want to blink a light every second. You want to set a timer to go off every 500 milliseconds. How do you configure that timer to do what you want? Remember, we've got 3 parameters here. We've got the maximum value that the timer can hold. We've got P, which is the pre-scaled value. So in my notes, when I use P, that means the pre-scale value. So P equals 1 means it's not scaled in any way. P equals 2 means it's cut in half, and so on and so on. So P for me here is a factor. Inside the application notes, it'll be represented as pre-sec or pre-scaler, and there they're talking about the 2 to the whatever power. So 2 to the 2 will be cut by 4. FC here is your clock frequency. This is the frequency of the clock that is driving that timer, is driving that peripheral. If you want this to be 1 second because the count wants you to, you've got to pick and select these 3 values. You have control over max to some limit in terms of the size of the register, you've got some control over P. You can go from 0 to 10 or 1 to 1024. Let's take a look at FC. So where does FC come from, and how do you calculate all of these things? What you're going to do is you're going to rearrange this equation to calculate some value. You're really trying to find value. You're really trying to find that value that goes in the top. So what you want to do is you want to rearrange this to say, well, 1 second at a certain clock frequency divided by some sort of scalar, that's going to give me this value that I want to put into my timer. The question that's going to come up is, what's the value of P? And for some choices of P, the clock frequency is either too fast or too slow. The clocking system on your Gecko, we lost my phone. The clocking system on your Gecko is actually a really complicated system, like distributing a clock in an embedded system. Let's see if I can turn this to make it look. The clocking system inside of any major chip is basically black magic. That you have to distribute to all the millions of these registers a clock, and all the edges have to be synchronized in the same amount of time. We're talking about they have to be synchronized in the orders of nanoseconds. All the traces that get routed through your chip, they introduce delays in the clocking system. So this clock system has to be well designed. In general, there is a clock management unit that is responsible for generating and creating all the clocks on your chip. There is one major external oscillator on your chip, and then the rest of them get distributed out to the LEDs, the LCD, all the peripherals through the clock management system. The high-frequency peripheral clock is the clock that drives all of the peripherals on the high-frequency bus. From there, the clock for each peripheral is broken off. So the clock for the timer, it gets routed from that high-frequency peripheral. And if you look down here, you have to not only enable the high-frequency peripheral clock, you have to pre-scale it, then you get to turn the clock on and off for your particular peripheral. So you've got this fast clock coming in that you pre-scale, that then you turn on, and then it eventually finally goes to your peripheral. So the clock is actually gated. So there's effectively an AND gate here that turns the clock on and off. If you dig down into it, you can dynamically change the frequency of the high frequency bus. You do that by sort of changing the band that the oscillator works in. By default, the value of this bus is 14 megahertz. If you want to slow it down, you can change this value. If you want to speed it up, you can bring it this way. The default value, the reset value, is 3, which means it's 14 megahertz. You really don't want to go changing the bus frequencies. Just if you don't need something, simply turn it off. It sort of gets even worse in the sense that if you were trying to set up the clock to your timer, not only would you have to pick the frequency of the bus, you'd have to enable the clock, and then you'd have to figure out how much that clock is actually disabled. Or actually pre-scaled. That's a lot of work for us to be dealing with when we simply want to turn on and off the timer. So what we're going to do in class is we're not actually going to mess with these bits when it comes to the clocks and the peripheral buses. We will use the clock management call to the CMU from the EM libraries to manually turn things on and off. So there will be a function call. Called clock frequency get or clock frequency set or clock frequency enable that will actually turn on the clocks and actually report to you the value of the clocks. So one thing you're going to do in assignment 2 is actually request the clock frequency, and it will report it back to you. You will see in all the labs and all the assignments that I give you that I've already set up the clocks for you. I just don't need you to deal with it. It's a function call to set clock and I just set it up so that you don't have to. But you can request the frequency of the clock and validate it. So in all the labs, you will have something that looks like this that's called clock enable, and that will set up the clocks that you care about. You have to have both of these lines. So let's say you're in your code and you're mucking around and you accidentally delete something and you can't talk to your peripheral at all. You write all these lines of code and nothing actually changes. If the timer is not enabled, he'll never listen to you. And if the bus is enabled, then you will never even get to the timer because your system will not be enabled. So make sure that both of these lines are always there when dealing with the systems. There is one final timer inside of the chip, and it's not a part of, let's say, the Giant Gecko system. It's actually a part of the ARM core. It's a 24-bit timer. It's a system timer. We will not necessarily use it because this is probably more used for a real-time operating system that would be on your ARM. And actually, none of your Giant Gecko documentation talks about system clock. So the way that your chip is manufactured is that ARM makes the core, ARM makes the CPU, and Silicon Labs makes all of the peripherals, all the timers, all the DMA, everything else. So if you want to know about a peripheral, you go to Silicon Labs documentation. If you want to know about the core, there is nothing in the Silicon Labs documentation about the core. It is all inside of ARM's documentation about the processor. So if you want to know about the system timer, you have to go to the Cortex M3 user guide. This is not a Silicon Labs product. Now, this will sort of get you ready for assignment 2 and also sort of for lab 2. We talked about a couple different ways in which you can use or access your timer. The first way is the dumb way. You can set up your timer to count to some value, and you can continually look at it until it reaches the value that you want. You are effectively busy waiting on your timer, and your processor is doing nothing better than looking at an integer that keeps getting counted. This is a way to count some amount of time, but it's not really effective for anyone's time. The purpose of having a peripheral is that you set it up to go off and do something else, and then it does it while your processor does other work. If your processor is sitting there just counting, it's wasting its time. You're better off writing a for loop with a fixed number of instructions and doing the math that way. Just busy waiting on the delay. Second thing you can do to measure if some amount of time has occurred is you set up the timer, and instead of polling on the value of the timer, you can sit there and you can poll on the value of the overflow flag. Some systems will do this. Again, it's just a busy wait to make sure that some amount of time has occurred. This is, again, a lazy way to use your timer. You're setting your timer up to count, let's say, 1 second, 2 seconds, and rather than looking at count, you're just looking at the overflow flag over and over and over again. This is also a busy waiting method, and this is not something you should use because you're just wasting cycles on your CPU. Option 3 is the way that you should really work with and handle timers. The idea is that you set up your timer to go off after some amount of time, and then you set up an interrupt handler to deal with that event when it occurs. So your compiler, your tool chain, will have an interrupt handler that will get called when the interrupt occurs. That's where you do all the work related to the interrupt. The reason that you do this is that your processor can go do other work while the timer's counting, or it can go to sleep. So if the processor's asleep and an interrupt occurs, it wakes back up, handles the interrupt, goes back to sleep. So if all your CPU is doing is turning off an LED on and off, it can go to sleep, wait for the interrupt, change the LED, go back to sleep. And it can save a tremendous amount of power. Option 4 that you can do is to get the processor completely out of the loop. So we've talked a little bit about the peripheral reflex system, about the DMA system. You can configure your timer to talk directly to another peripheral and do work for you. This lets the processor sleep the entire time and only the peripherals interact with each other. This is probably the most energy efficient operation, but it's also going to be the most complex to set up, and you also might have sort of limited abilities. There are only a limited number of things that a timer can talk to another device and do. So for basic tasks, you'll be able to do it, but not every single thing will you be able to accomplish sort of over the DMA, over the peripheral reflex system. In assignment 2, in lab 2, in assignment 2, you're going to try out these 3, just to see what they look like. You'll try this out, you'll comment it out, you'll be done. You'll try this out, you'll comment it out, you'll be done. Assignment option 3 is what you really want to do. Bless you. Lab 2 will be entirely like this. You will simply be using interrupt handlers. You will not have any code in your main once stuff is set up. You will not be busy waiting. Your while loop will be completely empty. Another note on interrupts. I think we went over this. I said it, but I'll have it up here on the slides. Your peripherals can cause interrupts. The interrupts are serviced if and only if the interrupt is enabled and the interrupt flag occurs. Both things have to be true. As soon as you enter the interrupt handler or the interrupt service routine, however you want to call it, you have to acknowledge the interrupt. You acknowledge the interrupt by writing to the IFC register and clearing that flag. Some older systems have special return from interrupt instructions. So there will be like RTI rather than like RTR. There's special assembly instructions. The tool chain automatically handles this for you. But the first thing you need to do whenever you enter an interrupt is you need to acknowledge the interrupt flag. Otherwise, you're going to be in that flag forever. So the idea is that if an overflow interrupt occurs, the bit 0 in the IF register will be high. That means you need to write a 1 to bit 0 in the IFC register to clear the interrupt. So this bit in IF is going to go high. You need to write a 1 to the corresponding bit in IFC to make it go away. Your interrupt handlers are already named for you from the compiler. So on other systems, you may have to use a assembly instruction or compiler directive to tell the tool chain that this function lives at this memory address, which implies that it's handling this interrupt. This tool chain does it for you. So in the memory map for the loader, it says that the DMA handler, the GPIO handler, and the timer 0 handler all live at a certain address. They've already defined this for you. So all you have to do is create a function with this exact name, a void function that takes no arguments, and the compiler will automatically call that function when the corresponding interrupt occurs. So these functions are already predefined. It's like magic. You write them, and if the interrupt's enabled, they get called. All of this happens because the software system that Silicon Labs developed and the compiler set that up for you. Other systems, you may have to set your own functions. You may have to write that function's address to a memory location. It just depends on the system. So if you want to use the timer 0 interrupt, you have to have a function that is void timer 0 IRQ handler void. It must be exactly that definition. You can't make it take a void star. You can't make it return an int. It will miss it and it will not match up to it. Remember, if you are dealing with the overflow interrupt, and let's say it's in bit position 0, then you need to make sure that you write to the IFC register such that you clear out this flag. So the IFC register has the exact same layout as the IF register. One is simply a flag, the other is a clear instruction. It clears that associated flag. If you don't clear that flag, you will sit forever, for the rest of your processor's natural life, in that interrupt handler. What I've got, and what we will do, for those of you who are done with Lab 1, you can start on, and continuing on through Wednesday, for those who have yet to finish Lab 1, we have an in-class assignment that goes over the timers. I set up these assignments to prepare you for the lab. So this assignment 2, and along with lab 1, will help you do lab 2. And as we were saying earlier, once we get through the first 4 lectures, and we get through the first 2 labs, then it'll sort of be exam 1 time. So once we get through that material. I have started posting the code on GitHub. So rather than post the code on Schoology, and then when there's a change, I re-upload it, I have posted the raw code on GitHub. And what I want you to do is to, every time you have an assignment, is there is a default project that you can import. It's called default CXX project. It's a C++ project. There are instructions on how to do that on the Schoology site. If you import the project, it'll give you a new project. Go to the source for this assignment, copy and paste the source in the main, rename the project, there you go. So every time you want to do a new thing, don't go to Blink, don't copy an existing project, import this project, rename it assignment 2, go to GitHub, and copy and paste in the code for that particular assignment. And I'll show everyone how to do that here in a second. Now, a couple people have reported sort of weird problems with Simplicity Studio. One problem. If you download the latest version of your computer, you try to import this project, they have changed the way the software development kit looks. You're going to get some errors. It's going to be super fun to deal with. 2, there's a bug in the install that Felix and I have encountered where it refuses to connect to the internet and download anything. I don't know the exact fixes. I've uninstalled it, reinstalled it several times, and then magically it works. The installation on these machines will work. Without problem, without fail. They should work. I've tried them all before the semester started. If you're out of hard drive space on one of them, like Felix was on his desktop, I call IT and they uninstall Autodesk or the stupid stuff they have. But you're free to use your own software. I'm happy for you to use your own software, but you might run into a couple bugs when it comes to just differences in toolchain versions. But in class, on these machines, should be sort of the easiest, simplest way. And I'm going to walk through right now this assignment. I'll show you sort of how to get installed, and then I will go around and we'll take the next hour and a half to do, hour 15, to talk about where people are on lab 1 and get started on assignment 2. Sound good?